Traditional hydrothermal geothermal projects can be very long-lived, with examples operating for nearly a century and relatively well-understood operational challenges like depletion, scaling, and corrosion. However, newer scalable geothermal concepts like EGS have additional operational challenges like fracture evolution over time, short-circuiting, emissions to the surface, and induced seismicity. While closed-loop systems pose additional topsides challenges associated with next-generation supercritical working fluids, long-term well integrity, monitoring, and maintenance. So, what are the challenges associated with each type of geothermal system, and how can those challenges be solved with new technologies, innovation, or technology transfer from oil and gas? What is the expected lifespan of the different types of geothermal energy systems? Let's explore.
Welcome again, everybody, to Pivot 2020. I am Jason Fisher, a geologist working as a consultant in the geothermal space, and I will be the moderator for this session. Today, we are joined by panelists from various backgrounds to explore geothermal well lifecycle, production, and operation challenges. Now, let's introduce our panel members, starting with Dr. Catalin.
Thank you, Jason. My name is Catalin Teodoriou. I'm a professor at the University of Oklahoma, and I bring today a little bit of my experience over two continents, Europe and North America, where I was involved with various geothermal projects, as well as oil and gas, of course, because my background is mechanical engineering and drilling engineering, with the main focus on well construction, well integrity, and actually making a better future for geothermal.
Okay. Thank you, Catalin. Pejman.
Hi, everybody. Good morning, afternoon, good evening, depending on where you are. My name is Pejman Shoaib-Omrani. I'm a senior scientist at TNO with a background in mechanical engineering and applied mathematics. For those who don't know about TNO, TNO is a research institute in the Netherlands, which is focusing on applied sciences. And I'm currently working in the energy transition unit, where we are looking into various energy commodities and how we can improve these energy systems and make them more affordable and efficient. My background, let's say my expertise, is mainly in the production optimization and flow assurance of the geoenergy systems. And my second hobby at TNO is to focus on the role of digitalization and specifically artificial intelligence in the geoenergy systems. What I'm going to bring into the discussion today is that I've been working in the topic of production optimization and flow assurance in the oil and gas industry for more than 10 years. And around 2016, I started to get into the geothermal topic. And for me, from the perspective of production optimization, this was at the beginning a very boring topic. Like, I was coming from this multi-phase flow and very exciting things happening in these oil and gas wells, and I get into the geothermal for the low entropy system single phase. So I was like, this is not going to be my thing. But during the years, I really got excited, and that's the angle that I want to bring, how we from the oil and gas sector can be excited about the problems in the geothermal and how we can improve that. So I'm very happy for this panel session, happy to be here, and I hope to have a very good discussion.
Thank you, Pejman. Fabio?
Thank you, Jason. So my name is Fabio. I work for WellTech as technical manager for completion operations. And WellTech is a service provider for the oil and energy sector. We provide solutions for completion and for interventions also. And my background is I've been working for almost 19 years now in the energy area. Previously with 18 years from an oil and gas operator, passing through R&D and operations and well design as a completion engineer, and joined WellTech last year, beginning of 2020. And we are working as we are in this transition also and starting to provide solutions for all other markets such as geothermal, CCUS, and so on. And I'm trying to share this experience from the operational background and the operator point of view with coming together with this service provider market. It's a different kind of perspective. So share with you guys, listen, and I hope, and I'm honored to join with you guys. Let's see, it'll be good.
Thanks, Fabio. Last but definitely not least, Simon.
Hey, thanks, Jason. Hey, team. So I am a resource manager at Ormat. Ormat's one of the leading geothermal companies that has both exploration, development, and operational fields. So we have about 1,000 megawatts of geothermal energy under operation, and that's in a combination of fields that are both low temperature, medium temperature, and high temperature. We have artesian, we have pumped wells, and we operate in multiple countries as well. So I have personally about 10 years plus geothermal experience, and mainly focused on the operational end. And I started my career as a geochemist, so much more focused on the scaling and stuff. So really looking forward to this discussion.
Okay, great. Thanks, Simon. Thank you guys for the introduction. Let's just jump right in, right? Geothermal fields are known to operate for long periods of time, and wells have long production and injection life cycles. What is the average geothermal well life cycle? What would you say are the top 2 operational challenges for geothermal applications? How does this vary based on geothermal field and technology, i.e. power production, i.e. binary, flash, and district heating, which is direct use? Let's start with Simon, and anybody else feel free to chime in.
Thanks, Jason. So yeah, look, from my experiences, geothermal wells we should be targeting that they should be lasting, 30 years of lifespan, and unfortunately, it often doesn't occur, in particular in the higher temperature fields. So why is that the case? Often that's because either through an issue in the well construction or design results in often the well's not handling a lot of thermal cycles. So the thermal cycling is something which we really have to minimize, but we also have to make sure that the wells are designed robustly to handle as many thermal cycles as we can. That'd be my first major challenge. And the other one, of course, is scaling. Scaling is something which occurs both on production and injection for different reasons. Typically, calcite scale on production end and silica scale on the injection end. But trying to clean that out or working on ways which reduce the stress on wells is a key challenge. And we're seeing a lot of technology evolution now for trying to clean out those sort of wells without creating thermal cycles, which leads back to that first point.
So being in academia, I have to start actually with definitions, because that's supposed to bring us to the same level. And, go in the field, in the oil and gas industry, and ask somebody about the life of the well. And you will find out that you get any number between 5 and 50 years with actually existing wells which are older than 100 years still running today and, being available today. So if we look at geothermal actually bring us with a very easy redefinition of life of the well. Because in geothermal, we know that we want to create something that will be like a power plant. And most of the power plants, they have a pretty, let's say, nice, easy way to define the life of the power plant, which will be probably 50 plus years. And that's a classical way to look at a well. And these 50 plus years bring us the challenge of designing something that, according to what I was able to listen in the past, days in this pivot 2021, is everybody is talking about making the well cheaper and lowering the cost. But I believe that we have to come back to the definition of the life of the well. And my favorite book of all, the book of Economides, is saying that actually we should design a well that will lower the cost for the life of the well and will not lower the cost at the time when we drill the well. So just to wrap up everything here, to your answer, if I design a well, for example, for district heating, obviously most of the houses in that district will be there for 50 years plus. So I should be able to design a geothermal system, including the wells, that will last for 50 years plus. If I design a power plant, whether it's a binary power plant or not, it doesn't matter. The well itself is the one that provides the fire, the heat to the power plant, and that requires again the ability to last another 50 years. We have Lardarello, and this is my last sentence. We have Lardarello producing geothermal energy for over 100 years. And we know that at least the geothermal resource down there will last 100 years. So that means for the future generation, if we want to shut down coal power plants, if we want to remove most of the other power plants and to bring geothermal as a competition, we have to design them for probably 100 years. Right now, that's what we know, that geothermal resource will last for 100 years.
If I may also add, I mean, I really agree with both Kathleen and Simon. Maybe in the case of a panel, we should also somehow disagree, but it's well said by both. Adding into with respect to the, let's say, for how many years we need to design the well, I think the 30 years is something that is kind of a design criteria. We never think about how we could actually extend that. And one of the ways that you can extend it, as very well said by Kathleen, is to think about the operational challenges that this well will have. This is not only the part that you're actually completing and realizing the well. This is the 30 years that this well has to overcome a lot of challenges like scaling, like corrosions, a lot of interventions, and that is really key in that sense. So I'm looking mainly from the direct use perspective, and I think it was in the first day by the Department of Energy in one of the sessions, they said for the direct use, one of the main criteria is the energy content, and that is determined by the diameter of the wells. So you need to deliver a certain energy content that has to come with the diameter of the well, and then you end up with large diameters. And what we saw in the Netherlands at the beginning of the geothermal growth in the Netherlands, everybody went with the single barrier. So no installation of the additional tubing. And also the corrosion problem has been quite underestimated. So with respect to the operational challenges, it's no surprise that corrosion always ends up as the first topic if whenever we're talking to the operators in the Netherlands. And I think also in some areas in Germany, like the Molasse Basin and also Paris Basin in France, they would also share the same thing. The second challenge to talk about, and then I'm gonna finish this part, is we are not here to only talk about the well as the, let's say, the tubing where we get the production from. We should not forget that one of the very major problems in the current geothermal system is the failures of the artificial lift systems and the ESP systems. That directly doesn't have an impact on the life cycle of the well itself, but has a big impact on the operational expenditures. And I would really like to also expand this discussion, also not focusing only on the well tubing and the casing, but also about the ESP, which is, and also the, let's say, the downhole pumps, which are really the heart of the production. So I would call the two production issues being starting with the corrosion, and the second will be the ESP failures.
Yeah, I had to say that I also agree with you guys. So basically what we're talking is that we have a lot of focus on de-risking projects just by reducing the cost of construction, like the CAPEX specifically, but we are not considering OPEX or maybe repurposing costs in the future. So we know that geothermal wells, usually we plan to have them lasting for decades. And also at the end of their lives, they could be repurposed to another application. So we need to think, I guess, that is maybe rethink how we design the concept of the well design of the wells that could provide more flexibility to last, more, to extend the life of the well. So what kind of problems make us, for example, shut in wells prematurely? So is that a fifth zone? That's the case. So how can we control that in the future? So how could we build a concept well that will provide you flexibility to, in the future, manage the issues that we start to face? And the second point that I think is essential, and I still don't see, that kind of traction, is we need to, sometimes when we talk about innovation and implement technology, people always tend to think that we are talking about more expensive solutions. But actually, we should think that innovating usually leads us to reducing cost in the long term. So of course, we need to invest a little bit in the beginning to design and develop new products and research, and we need to do it, and it costs money, but we probably provide us some kind of equipment, some kind of product or material or whatever that in the future will reduce our OPEX, as Pejman said. So what kind of material? We know that we have a lot of metallurgy today that could last for 20, 30 years maybe, but they cost too much. So how can we reduce the cost? Do we need a new material? How can we innovate more? So I think that this is the biggest problems in my point of view. So a method to think and rethink the concept well design and apply more innovation with more R&D more aggressively. I think that we need to, this is the decade, right? So let's do it.
All right, thank you. All great points from the panelists. We're going to address.
If it's all right, Jason, I might just add into something that Pejman talked about, which was pumps, because I think that's a really important point. Is we've seen over the last few years, quite a bit of innovation in geothermal pump technology, in particular for power generation. But often it's and that innovation has been, how do you lift more from a well, and also how do you make it able to handle higher temperatures. And there sort of has been a bit of a gap between artesian well flow and pump temperature capability. So I think that's a gap that we have to fill. But from an operational standpoint, Pejman, we as a company at Ormat have a lot of pump experience, and one thing that we've ended up doing is actually basically building and designing for a lot of line shaft pumps to help take away that risk of ESP failures downhole, and being able to lift more volume. That's probably been something that has happened over the last sort of 5-10 years, is just getting bigger and bigger line shaft pump technology that can handle higher temperatures to reduce that failure mode. One of the other things with pump technology that we sort of touched on at the start was about scaling, and one of the major benefits of keeping things in solution is keeping it pumped and under pressure is it keeps a lot of the scale risk down, and that means that you can actually, at least for power generation and for direct use, it actually simplifies the overall process a lot, because you don't have flashing and you don't have the driver to create as much scale as it otherwise would.
Yeah, no, Simon, I mean, this is of course a very nice discussion, because that's where we are going in the kind of sharing knowledge and experience from the power generation to the direct use. I mean, as you said, of course, ESP's failures, one of the alternatives will be to kind of get rid of all the downhole electrical failures, is to use the line shaft pumps, and that's definitely is a robust solution. From the perspective of the direct use, since you're gonna realize the systems in the urban areas, one of the biggest challenges, of course, with respect to the noise of these systems, and that's one of the things that we are definitely looking always for the alternative solutions. It's not only ESPs. There are like tens of artificial lift systems and pumping systems you can use, and line shaft pumps are being used successfully in a lot of high entropy systems. So one of them is the fact of using line shaft pumps, which would probably will not be acceptable in the urban areas. That's one of the, let's say, the current discussions. And the second one is that the operation of the systems are very different. I mean, looking into the direct use, everything is demand driven, and you have what we call the bathtub curve, to have a high demand in winter, low demand in the summer, and that is something that your pump would not like anyway. So that's a kind of a known problem, and we can definitely learn from oil and gas, from unconventionals, from all sort of cases where they do see this sort of a decline in the production, and the ESP has to accommodate for that. But I do believe these are the two areas that we can look for how we can make the ESPs more robust to these variations in the production rates. And second, if we want to look for alternatives, where I would really look into you, Simon, and also a lot of similar companies who are expert in these line shaft pumps, is how we can make them available also for the district heating, and especially in the urban areas, how we can make them happen.
Right, but here is something that you know, I have to come back to the price, cost, and everything like that. So one of the focus of my research group is that we are looking on the let's call it multi-body dynamics of downhole systems. It could be a pump, it could be a line shaft pump, it could be a drill string. And we are trying now to understand a little bit in detail the idea of these vibrations. And some of these vibrations will create noise. Some of this vibration will end up with destroying the pump. And altogether, actually, if we understand them, will allow us to create better systems for the future, but in the same time to minimize the maintenance cost by, for example, retiring a pump before the pump fails. Because once, I mean, there are some costs associated with a failure into the well, and there are some other costs when you are just removing the pump and replacing the pump while the pump is still, let's say, in acceptable condition, so no breaks, nothing fail on that. And here comes with something that I also hear, I think it was today and yesterday, about downhole sensors, about artificial intelligence. Obviously, everybody is doing that right now on getting more data. But we need to you know, convince also the geothermal industry that we don't have to stay low cost. By adding a lot of sensors in your system, you'll be able now to improve the operational phase. And in the same time, you'll be able to lower the cost for the future by knowing the behavior or understanding the behavior of, for example, one of my really big focus is actually very deep line shaft pumps, and trying to upgrade the line shaft systems in such a way that actually you can lower your pump to a level that was never reached before because of all the mechanical limitation of the current line shafts. But that means, again, and actually Robio says that innovation doesn't mean increasing cost, which actually that's the idea. An innovation today may be expensive, but it's not expensive later. And one of the things that I would like to bring up here is that I always like to consider geothermal as the nuclear power plant versus a coal power plant. You know, a nuclear power plant is designed actually that you don't have to go inside of the reactor. It's designed to operate in such a way, and that inside of the reactor will be now what is downhole. We have to create that downhole. I mean, there is no fear to learn from oil and gas, but I believe it is time to move away from oil and gas by making it better, by expanding the knowledge that oil and gas has bring. And believe me, more than 100 years of oil and gas is amazing as a knowledge, but geothermal needs that step further, where, for example, let's build wells where we don't use cement, because we have learned from every single geothermal well that the cement fails. So why not changing that? Of course, it's very difficult to do it now because the regulation doesn't allow you to do that. But in the same time, if this innovation will be, you know, will come forward, we should be able to move to the next step. And one of the things I've learned from geothermal so far, which is, I'm trying to be now the negative part of this group, is that a lot of geothermal projects have failed. And people are afraid of investing in geothermal because they have seen or heard, and that geothermal failed, and so on. And if you look on all these, let's call it failures, but they were, let's say, unsuccessful scientific approaches, the way I like to call them, those unsuccessful stories are actually having one thing in common: low cost. Everybody was budgeting geothermal on low cost. And for those of you who have actually watched the break, you know, when you're saying coming soon in this pivot 2021, have you noticed that actually they are using chain and API tongs to make up a drill string in 2021? I mean, I was born in the year when the first top drive came on the market. I will not accept today that a geothermal well will be drilled without a top drive. I will not accept that today a geothermal well will not use the latest technology in drilling. And this is, I know people cut costs, but costs are not the cost we are looking now. We are looking the cost in 50 years.
Okay,
And
great stuff. Great stuff, Katalin. Let's keep the conversation moving. A lot of you spoke about well design as a major challenge in geothermal development. So how important is it for us to develop a geothermal well design standard for our industry? And how has well design construction and completion changed over the last 100 years of geothermal production?
Maybe I can start with this because it's a straightforward answer. Actually, it is necessary to have this, let's say, well-designed standards. And I think we in the Netherlands, just a few months ago, we published the first standards for the geothermal well designs because we saw there is a need for that. I mean, we see that it's, I think, Katalin brought it as the, let's say, the negative side that these projects are failing. To give it a bit of, let's say, maybe more positive vibes, is that there is a struggle. And that struggle is not because we don't have sufficient resources, it's because now we start with the very being optimistic about it. And after a few years, we see that the operations of these systems are difficult. Like, as I said, everybody at the beginning in the Netherlands went with the single barriers. And then just if you get a corrosion, the cost of the patching, the cost of, let's say, renewing the tubing is just going to be quite a lot. And now we saw that with these new standards, they are asking that you have to go for the double barrier. And that's, let's say, one new side of that you will see that in all the new wells, that is something that all the, let's say, operators and the design companies are take that into account. We see one other side of the innovation, which also goes into the non-metallic tubing. So you're seeing a lot of composite and the GRE liners, which are now getting quite popular in the geothermal industry, so that you can minimize your corrosion issues in the wells. And I've seen operational cost of the wells with GRE liners, which are way below the conventional wells. Even they go for a much higher investment cost, but we saw that the OPEX is way below. So that already in such a short time, you see that this is already paying off. And the last part, so we talk about the conventional ones, we talk about the new wells with the double barriers. And one thing that we should not forget is also the end of life and the abandonment cost. And that's one of the things that, for instance, I mean, in the Netherlands, we have this rule that you have to install a second tubing and monitor it for 20 years in order to protect the drinking water area. And that will be an additional cost. So if you already can design your well from the beginning to take into account that abandonment costs by already having, let's say, a tubing installed and all the monitoring systems in place, you can already gain that cost easily during the lifetime and the abandonment time of the well.
Yeah, so it's interesting to see how we can notice that things are all connected, right? So Katalin started talking about like monitoring ESPs and other kinds of pumps, so we can check the health of the equipment and maybe change and plan the workover in advance, so we reduce the OPEX, because it's a planned operation, it's not a remedial operation. And this is also applied totally for the well itself. So what kind of information we have from the wells we have so far. So we really don't monitor them almost at all, right? So we just run the casings, we do some calculations, and we open to production until they fail. And then we go there and try to remediate. So this kind of, as Kathleen mentioned, so if we could do all this completions and casings and liners in open hole, for example, could we have some kind of sensors in the analyst that could provide us some information from, and if you have some isolation in the zone, so could you have different information for each zone and maybe identify remotely which zone is the cold zone and is, you know, stealing your heat? So could we close that? What kind of technology we need? So could we have a autonomous flow control port, I don't know, that closes with temperature, lower temperature? So what kind of really innovation and new technology could we think about? Is that something that we need that doesn't exist? Can we apply something that is already used? So why not we use some tracers and the analysts so we could check which zone is it's hot and cold, or is producing more or producing less. This is all connected. So, and then we go back to the well design and how we plan the wells and how we design the wells, thinking in the OPEX and also in the abandonment. And the abandonment will maybe mix together with repurposing. So we talk about repurposing wells from oil and gas, but how can we maybe plan our wells to be flexible to repurpose within geothermal? So could we start using them for one specific application, and maybe in the end of the life, if the efficiency or the flow rate reduces, could it be applied to another application? Can we think about repurposing within the geothermal life cycle, lifespan? So this is all connected, and if you don't plan this in advance and you don't have your well ready for that, then your costs of your workovers and your interventions and your abandonment will, of course, have a much higher cost. And that's why we see a lot of discussion and webinars online talking about reducing the risks of the projects just by reducing the cost. But if you don't consider OPEX in this analysis and you just try to go down and drop the cost, then your project might be approved, but then after 2-3 years, your pump will fail, and after 5 or 10 years, your casing will park. And then you need to do a heavy workover and do a relining and run another casing inside, or maybe run a completion string, and then you add more 50% on your project that was not planned. So that analysis that you've done in the beginning, it doesn't work anymore. So you have a new well inside the well that you designed before. So yeah, that's all connected. That we need to plan in advance the best we can, and for that, going back to the standard as Jason asked. So the standard is a basic guideline, right? So as the experience, as Simon mentioned, the experience, and Kathleen also, the experience from the oil and gas with a lot of standards, it proved to be, a winner solution. So how can we improve that? So we need a standard, and maybe not only guidelines, but maybe a method or a proposed method, an agile method, because we know that the industry is moving even faster and faster every year. So how can we have an agile method of designing concept wells that can be fit for our, more swift environment that we lead now? So everything is changing, temperature is heating. We have a lot of, pressure to move faster. So we need to be prepared to do this.
Yeah.
Anything to add, Simon?
Oh yeah, it's I think there's sort of, when we consider that there's two types of wells, right? There's the higher temperature geothermal, and I'm going to sort of park that to one side. And then there's the other one, which is your ability to be more cookie cutter in the lower temperature space. But overall in geothermal, the difficulty is that many individuals, it takes a long time to design a well, to build the well, and then to actually operate it and actually capture those learnings over the life cycle of that well as an individual. And it means that when we're trying to bring people into the industry, we have to be able to let them see all those lessons that have been learned in the past and allow them to apply it. So that's probably one key challenge, I think, is often we don't have a lot of discussion that enables people to learn at a rapid pace and to learn those lessons from others. From a perspective of standards, there's actually very few international standards for geothermal well drilling and design. And one of those is probably NZS 2403, the New Zealand standard. And that's been picked up in a number of different countries as well. But one of the downsides of standards is it potentially limits innovation. And that's the difficulty that we face, is making sure it's applicable. And maybe it's not so applicable for those lower temperature well settings, but also is how do we make sure it gets updated frequently and it's up to speed with all the latest developments and innovations. So, and Catelyn touched on a very important point earlier, which was, if you have a failure, it's bad for the industry. And so we've talked about project failures, but if you have well failures, then that's really difficult to overcome as an industry. So having standards is very important, just to help prevent that.
Ellie?
So Simon, that's the moment I have to be, against what you are saying about the standards by limiting innovation. And I will try to give you 2 examples that we have learned pretty hard from the oil and gas. Number one, in oil and gas, we have learned that actually being transparent will allow the industry to thrive. And in the past, there were a lot of things that happens down there that people or companies were not sharing with public, with people. And that was where, this industry kind of got a kind of a shadow light because we are not having the transparency. And all the companies I've seen in Pivot 21, I've seen in a lot of conferences, all big companies are trying to be transparent, to show what they are doing, to show how much this industry actually cares about well integrity, about environment and what is down there. But then let me give you a short example about why setting a standard will help you fantastically in geothermal. According to oil and gas, we design wells that will end up with 7-inch casing down there. And this is in every book, every single class that will be taught in oil and gas or petroleum degree, they will have the same schematic with 7-inch down there. But when we design geothermal, we design the geothermal wells for flow rate. So the 7-inch doesn't make sense anymore because we might need much more than 7-inch. We need 958-inch. This is what I wrote about 15 years ago, that we need 970-inch casing for good geothermal wells to flow. But more than that, if you look at the materials, is that the current API standardization tells you about, just to take the very simple J55. A J55 steel is actually a steel about you have no idea what is its chemical composition. So therefore, a J55 steel produced in a country A may be corrosion resistant, whereas a J55 produced in another country will not be corrosion resistant because the standard doesn't specify accurately what is the composition of that steel. So if I want to move to geothermal and knowing the scaling and corrosion is a problem, I should be able to specify accurately what type of steel I should use in that well. And instead of J55, I should have, like in mechanical engineering, a very clear definition of the material composition. If we want to have a standardization, the standardization have to allow the engineers, and I agree that innovation is important, but have to allow the engineers to choose between some materials, but in the same time has to impose the limitation, for example, of having dual barriers, or having protecting the shallow water horizons and everything which is important for that. So this limitation, and I believe the New Zealand standard is doing that very, very well, because we don't want to have any incident with geothermal wells, because the moment those geothermal wells will start leaking the way some of oil and gas wells are leaking, you have to abandon them. And this will be where the cost will increase. So that's why the new standards, we have to learn from oil and gas. Oil and gas have done a lot of work. If we take them and we move to the next level, I bet that the standardization will help us to bring more innovation rather than bringing constraints on some. Of course, no standardization will tell you whether 7-inch or 9/5/8 is necessary, but they will at least tell you what are the minimum properties of cement, of casing, of tubing, and so on to use that one. And I will conclude here with another aspect of standardization. Most of the fiberglass pipes, composite pipes, which are used in the well, has never been fully tested in the environment down there. And I've done some research, but I know that there are a lot of published research that have shown that a lot of composite pipes will fail because of the elevated temperature exposure in time, and they will have a very limited lifetime downhole, which could be a problem if we don't create a standard where you say, okay, a composite pipe to be used in geothermal must withstand, I don't know, 5 years of 200 degrees C.
All right, thank you.
Yeah, I tend to agree with Catalin on that. So one of the things I suppose when I talk about standards and limiting innovation is where potentially standards very prescriptive and not outcome based. And I think that's probably where I see some standards, fail, is you end up having something that's 20, 30, 40, 50 years old that wasn't talking about outcomes, it was talking about one way. So I like your approach of making sure things have got options and things have got outcomes.
Okay, all right, that's great. Let's switch gears a little bit and go and talk about scaling. How does scaling differ from power production systems and district heating systems, and what well intervention techniques are currently being used to handle scaling, and what improvements can we expect to further improve or mechanical cleaning of scaling, and what technologies can be transferred from oil and gas to help deal with well intervention for geothermal?
Yeah, if it's right, I might kick this one off, which is, basically there's, we typically see calcite scale risk on the production side, and that's predominantly the main form of scale. Even now and then you get a field that's got a bit of something exotic, maybe a little bit of seawater input. You see that a little bit in Iceland. But basically, the major way of controlling that is through inhibition before it flashes, or by keeping it in solution. And then on the other end is, once we've taken a bit of heat out, we see basically two major scaling potentials, and those are typically silica or polymorphs of silica, which often limits the amount of temperature we can take out. Or alternatively, it is sulfides of some nature, whether it's in traditional geothermal, it's been antimony or arsenic sulfide, but typically they're really low concentration, and a lot of the focus has been on silica treatment or management at the expense of those sulfide scales. So, there's heaps of ways that we've been dealing with them, and one of them is how do you just prevent it from occurring in the first place? So, through chemical treatment, like I mentioned, inhibition systems, those inhibitors have to be able to handle the temperature and not get cooked. They actually have to be proven, and sometimes they can't handle running down the tubing and being cooked on the way to their delivery point. And then what we're seeing around silica is we're seeing much more focus on pH modification becoming an option to take more heat out, and that comes with its own challenges on the well design, because now we've got pH 4 or 5 fluid compared to pH 8. So what I'm seeing is a lot more innovation on the surface to take more heat out. So on the injection end is HF jobs or mechanical cleanouts, and on the production side is a lot more people starting to think about how they can use coil tubing and do live well cleanout, so the material doesn't drop down the well, that it comes out through the well, and that you don't have so many thermal cycles. But that's my view.
And your thoughts?
Yeah, I can also then maybe add the perspective from the direct use. So indeed, also a lot of let's say calcite-based scaling in the production side, and where we see most of this problem happens when you start to get, let's say, the your system goes through a degassing. So that's mainly is going to happen more towards the surface, where you, especially, I mean, so again talking about the Netherlands case, where we have a lot of CO2 dissolve in the water, and as soon as you get them out of solution, the change in the pH will lead to a scaling. So that's, I think, similar also to what Simon said, that one of the let's say straightforward inhibition technique is just to keep the system under pressure, make sure there will not be any CO2 degassing, and you can in that way control your calcite scaling. There are also a lot of sulfur-based and barite scaling as well, which mainly happens in the heat exchangers. That's kind of a temperature-driven scaling, which is also being observed quite a lot. And that requires a kind of a heat exchanger service. We don't see that much silica deposits at this point of time in the low enthalpy systems. But one of the other things which is also quite a challenge at this point is the production of the norm, so the natural occurring radioactive materials, which they would also deposit. And I think this is not something new for oil and gas. But why is it interesting, and why I start to become quite enthusiastic about the geothermal part is like the amount is huge, because now we are producing 400 cube an hour, 350 cube an hour. So the amount of norm that you have to deal with it, which will deposit in your filter systems. So you have to, let's say, in principle, treat your filters, or let's say store it somewhere, and these are the radioactive materials. So that is very, very important how to deal with it. And that's currently, because the regulations are very strict, that also is one of the challenges in the industry. So I would like to maybe invite all the panelists, or even people listening to us, that coming up with solution to handle norms, keep them in the solution, is something which I think industry is now looking for it. And not with a lot of amounts, because again, the flow rates are high. So if you have to also put quite the ppm of these materials, that would also not be financially viable. So this is where I see kind of an overlap with the high temperature systems and the low temperature, where we have some similarities as well.
All right, thanks, Pejman. In the essence of time, we'll start to take some questions from the audience. The first one is, let's say, how much is corrosion concern reduced with a closed loop geothermal well installation with a CO2 working fluid? Any quick answers?
Well, CO2 corrosion exists whenever we have a liquid phase, water. So the CO2 dissolving in water creates the carbonic acid and creates the acidic environment. So the idea of a closed loop actually comes from the use of a clean fluid, of a known fluid, which avoids scaling and corrosion inside of the pipe. But outside of the pipe, you are still exposing the pipe to the environment, whatever it is down there. So corrosion may exist in a closed loop system as well.
Okay, great. Next one, can the panelists each give their opinion on the number one technological advancement needed that would make the most impact in improving well life cycle and performance? Just one needed technology. Each person just shout out that technology.
For me, it's reducing thermal cycles.
Reducing thermal cycles. Fabio, anything?
Yeah, I think there's thermal cycle is a good one, but also material development engineering would be important. They are all connected, right? We can mitigate corrosion, and we can also help reduce scaling that will lead us to reduce interventions. So I think material is key.
Pejman?
I would go with materials, and if I can have a small second one, will be about the pump advancement.
Okay.
I think I will say monobore wells, monobore drilling. It was one of my favorite projects back in Germany. And that involves materials, but with a monobore drilling will allow you to achieve any resource, anytime, and you have the best material in the well.
Okay, another one is there currently a way for entities to share information about operational challenges? Pejman?
Yes,
Yes.
actually, we were also currently in setting up such a platform, because whenever it goes about the subsurface data, usually you have these geological surveys responsible from each country to store that data and make it also publicly accessible. When it goes into the operational part, these are confidential data. This is associated with the production, with the failures, and this is often the things that people would not like to share, even though there are a lot of information content that we can learn from that. So currently also within our organization, we are looking for such a, let's say, secure platform to share this information, operational information, even, up to some level of time series data between the operators, where they can learn from for instance, the failure trends in the pumps or the clogging trends in the filters. And that is the way that we can really learn from each other. So we are definitely looking into it. And I think at this point of time, up to my knowledge, we don't have such a platform at that level of detail and resolution. But I don't know how the other panels look into it.
I can mention here actually one of my current project on cement. We are building currently the largest, the only database available on cement for long-term investigations. So we are collecting data on cement for my dream is to get 15 years of cement samples and looking how they behave in time. And I believe a synergy between industry and academia will help sharing these informations. Even some of them are confidential, but we can drive those platforms. I'm using a lot of cement recipes that I don't share the content of the recipe, but I just share the typical data and saying, okay, cement A is changing so nice with the temperature or with the pressure.
Yeah,
Thank you.
that's
You want to
good.
add something quickly, Fabio?
Yes, real quick. So I think also some workshops, we can see there are a lot of webinars are raising now in this, and the subject is being very, important. So we're gonna have the first SPE workshop talking about geothermal at the end of this year, hopefully, depending on COVID situation, of course. But this is a good, a good move of SPE organizing a workshop to discuss geothermal challenges. So we have a call for abstracts open now. So I think this is also an opportunity to discuss a lot of technologies to do wells that are more flexible and provide zonal isolation control, this kind of flexibility to extend the life.
Okay, great, thank you. Final question before we wrap up. Can you compare the expected life cycle of hydrothermal with EGS and what is predicted for closed loop geothermal systems?
I can start with the fact that hydrothermals may not need too much fracturing or hydraulic fracturing. So that means they are not going through cycles of cooling, heating. Therefore, the hydrothermal may last a little bit longer from the fatigue lifetime of the casing. However, scaling could be a problem. But we should not forget that EGS are deeper wells in a much harsher environment, and actually the biggest challenge of those EGS wells will always be fatigue of the tubulars and of course the cement.
Simon, you wanted to add something?
Yeah, look, the whole point of us doing what we do is to take energy out. So we have to make sure that we're designing wells that can actually transfer a lot of heat. And so, you could potentially design a well, but that lasts a very long time, but it may not transfer much heat. So I think it's a trade-off, hydrothermal systems, higher temperature systems, they can transfer a lot of heat, but they also have a few more operational challenges around them, potentially the fluid type and everything like that. But that is ultimately the trade-off, and that's one which it'll be interesting to see how these closed loop systems work, long-term life cycle cost, just in terms of just getting that amount of heat out.
Okay, that's good. Pejman, any final word on that one?
No, not really. I mean, I share most of the thoughts over here, so nothing really to add.
Okay, all right, great. Well, everyone, looks like our time is coming to an end. I'll ask each panelist to share their final remarks addressing geothermal operational challenges, and then we'll wrap up. About 1 minute for each person. Let's start with Simon.
Yeah, so for me, you know, look, I've come from a traditional geothermal high temperature artesian flow from New Zealand. A few years ago, I joined Dormant, and I've really had my eyes opened around the lower temperature space and pump technology, and how easy it is to cookie cutter, and how it makes the whole process a lot simpler. So that's been really awesome experience for me, and I reflect on that as an industry and go, there's a lot more low temperature spaces around, and therefore, you know, it's a space of innovation as an industry, which is going to enable us to take it forward. So well design, pump technology, and everything is really important that we innovate in that space. And I'm looking forward to seeing how quickly that innovation can occur over the next few years.
Pejman?
Well, first of all, I really enjoyed this talk, and as we also shortly discussed with you, Jason, I think this session that we had was probably one of the few ones in Pivot which really goes into the operational things. What's going to happen from the moment that you start production? Maybe we need part 2, 3, 4 also for this panel. For my last remark, what we see is that the one of the very important gain is how you're going to operate the system the next 20, 30 years. So if we would like to make sure that the cost of the system during its lifetime is minimum, let's get the production technologies, let's get the production chemists from day one in the design process, because they could give hints about how the system is going to be operated in the next 20, 30 years. We talk about 30 years of wells. I want to get back to the first comment of Kathleen, that when we talk into built environments, the houses are not going to be there for 30 years. They're going to be for much longer time. I'm living in an area which is gas-free, natural gas-free. It's heated by the heat networks and with 3 geothermal wells, which is in the neighborhood. So I hope that I don't have to see every 20, 30 years, there is, let's say, few other drilling rigs to get rid of this well and put a new one. So I wish that we can go for the longer lifetime of the wells. That's going to also impact the area where I'm living at.
All right, thanks. Fabio?
Yeah, I would say that this is the methodology of designing wells, thinking of the whole life, not only, you know, isolating the discussion to and summarizing the discussion to drilling challenges. Of course, we have, and we know that we have a lot of challenges in drilling, but we need, instead of thinking the well from the outside in, so we're drilling and then we put something inside. So let's plan our wells from the inside out. So what we need to do inside, how long we need to have them working, what can we provide to extend the life of the well. So then we know what we need, we know the requirements. So then we start to build the well from the inside out. So then we're gonna probably, most likely, reduce our costs during operations, optimize operations. We will optimize well construction also. We potentially will reduce the time of well construction, because the design of the well was thinking from the inside out. So I think this is the last message. So rethink and try to provide flexibility so we can extend the life of the wells. So again, we have a lot of wells that we need to shut in prematurely because we have a feed zone and we cannot identify which zone is the code zone, which zone is the feed zone. So how can we isolate and provide flexibility for the life of the well so we can control?
Great. Kathleen, your final remark, and then I'll just wrap it up.
Okay, I will probably say what I tell all the time my students, is that geothermal is beyond oil and gas. Geothermal is taking the absolute best of oil and gas and will create a better future for all of us. But we have to learn from what we've done in the past, and what oil and gas came out was the life of the well and the definition of how a well will last. We know that, and actually we have to think differently. We have to think in a way that will make these wells to go beyond 50 plus, and actually keeping the world running on energy, because either oil, gas, or geothermal, we talk about energy. And that energy is to allow our laptops to be on, to allow our panel here, our fantastic panel today, to chat each other and to disagree whenever has to disagree, and to hit our home. So I think that we just have to go forward, innovate, and make geothermal to be the next joint venture for oil and gas companies.
All right. All right. So thank you to the panelists for being here today and for the great conversation. I hope you, the audience, gain some great insight, and I hope we keep this conversation going. Finally, I want to thank you, Jamie, and the Pivot 2021 team and the production crew. Have a great rest of the day and enjoy the rest of Pivot 2021 for the rest of the week.
Thank you all.
Thank you.
Thank you. Thank you, Jason. Thank you, Jamie.